All right, so I'm going to second take. I really don't want to print out these pages again. Hopefully you can read along. Uh, section 2.5, section 5.2 today, polynomial division and the division algorithm. We talk about the division algorithm and the remainder theorem, polynomial division and synthetic division, construct polynomials with given zeros. Or constructing polynomial with given zeros. So the division algorithm is as follows. So let P and D be polynomials where D is not equal to 0 and the degree of D is less than or equal to the degree of P. Then there are unique polynomials Q and R such that P equals Q times D plus R. And so we say P is the dividend, D is the divisor, Q is the quotient, and R is the remainder. So if we write this in fractional form, we'd get P over D, our divisor, equals our quotient plus our remainder over our divisor. So you can see I got that backwards earlier. Now, how would you look at it? So this may not seem relevant right now, it may not seem related to division that you know, but what we did is we turned something that's a fraction, instead of talking about division, we're talking about multiplication and addition. So that's why we like to look at it this way. So if we were going to divide 13, so just using regular numbers, if we're going to divide 113 by 3, how we do that? We do long division. So we'd have 11. How many times does 3 go into 11? It goes 9 times. Subtract, you get 2. How many times does, you bring down the 3, how many times does 3 go into 23? It goes in 21 times. You subtract, and then that 2 comes down, that's your remainder. So now you rewrite 113 over 3 equals 37 plus 2/3. And so now we could rewrite this using the division algorithm. We could rewrite this using the division algorithm and say that this is going to be equal to 113 is now equal to 37 times 3 plus 2. And so these are algebraically equivalent. These are the same expressions. They express the same concepts. Only now, instead of talking about division and getting fractions back out, I have no fractions, and I'm just talking about multiplication and addition. So that's why we like to write it like this. It's easier to look at. And you can see some more interesting things that you can see from this. If R is equal to 0, the remainder is equal to 0, then the dividend is equal to the quotient times the divisor. And we say that D and Q are factors of P. We can also write that our dividend, our polynomial here, is equal to our quotient times the divisor plus the remainder as the fractional form, which I wrote before. P over D equals Q plus R over D. If R equals 0, there's no R over D portion. That's 0. So basically, if your remainder is 0, then you have two polynomials that are factors. We are the polynomial. So we're going to divide this out, and this is actually going to be some long division here, polynomial long division. We'll find a faster way to do it when we don't have, when we're divided by linear factors. I don't know if I'll have enough room on this page. We'll see. 2x. So I'm dividing 2x to the 5th minus 5x, and this is to the 4th. That's a typo. To the 4th, x to the 4th, plus 7x to the 3rd minus 13x squared plus 3x plus 6. And we want to divide that by 2x squared minus 3x minus 2. So looking at this, if the numbers get too jumbled, I might change colors. We'll see how it goes so far. So what do we do with polynomial long division? We do what we always try to, and then we try to get rid of each term as we go. So we're going to try to get rid of our x to the 5th power. So we're going to multiply 2x squared by, and then we're going to multiply that by x to the 3rd. So if we multiply x by the 3rd, and we'll get the following, 2x to the 5th. So I'm going to multiply this right here. I'm going to multiply each term. And I'm going to write it underneath here. And so that's going to give me, is it focusing okay? So it's x to the 3rd times 2x squared minus, and now I'm going to get 3x to the 4th. Notice my columns are lining up my powers of x's. And then x to the 3rd times negative 2x. So I got x to the third times negative 2. So I get negative 2x to the third. Now here's the interesting part. When you draw a line, you need to go and change all your signs. So I'm going to draw this line because we subtract every step like we did with when we were dividing regular numbers. We're going to subtract it every step. So when you draw this line, that's when you change your signs. So I'm going to change those signs. So I'm not keeping track of trying to subtract a negative number from another negative number. It's easier just to do this now. What should happen is you should get a 0x to the fifth. You don't have to write this term, but this column should zero out. If you don't zero out this column, you didn't pick the correct thing to multiply by, or your multiplication was errored. And then we're going to get over here, we're going to get 2x to the fourth. That's minus 2x to the fourth. And then we're going to get plus 9x to the third. I have two terms here. This one doesn't count, that's zeroed out. But I need three terms, so I'm going to bring down this negative 13x squared. Now, if I was missing any powers, I'd have to skip a space. But here I have all my powers represented, x to the fourth, x to the third, x squared, so I don't have to skip a space in writing my polynomials because I want all my columns to line up. I want an x to the fifth column, x to the fourth, x to the third, x squared, x, and then my constant column. So now that I've written this out, I'm going to take, what do I need to do to get rid of this term, this negative 2x to the fourth? Well, I'm going to have to multiply, I want this to be identical, so I'm going to need to multiply this by negative, and this is x to the fourth, that's x squared, I'm going to need negative x squared. So I'm going to say negative x squared times 2x squared, and that's going to give me negative 2x to the fourth. And then I'm going to have negative x squared times negative 3x, and I'm going to get positive 3x to the third. And then I'm going to get negative x squared times negative 2, and that's going to give me positive 2x squared. Alright, and once again, when we draw our line, that's when we change all our signs, and that should cancel out our first term. It's a plus, this is a minus, this is a minus. And so that's going to give us a 0 here. Then we're going to get 6x to the third. This is going to be minus 15x squared. Once again, I need three terms because my polynomial over here has three terms. And so with this, now what are we going to do? I need to get rid of this term right here. So I'm going to say I need to multiply 2x squared by, to get 6x to the third, I'm going to need to multiply that by positive 3x. So now I'm going to get 3x times 2x squared. So that's going to give me my 6x to the third. 3x times negative 3x. So that's going to give me negative 9x squared. 3x times negative 2. That's going to give me negative 6x. And so once again, when you draw your line, that's when you change all your signs. And so that's going to give us 0. And then we're going to have, what are we doing here? 9 plus 15. So that's going to give us a negative 6x squared. This is going to be plus 9x. And then I bring down that 6. So now I need something in this constant. I need to multiply a constant that's going to help me get rid of this negative 6x squared. So what do I need to multiply 2x squared by to get negative 6x squared? I need to multiply that by a negative 3. So negative 3 times 2x squared is going to give me negative 6x squared. Remember, these terms have to be identical until you draw your line. And then negative 3 times negative 3x is positive 9x. And then negative 3 times 2 will be positive 6. You notice something nice happens when I draw my line and change all my signs. I get a remainder of 0. So it turns out that when I divide these two polynomials out, my answer becomes this polynomial right here. So if I take these two polynomials, this polynomial right here and this polynomial right here, so if I take 2x squared minus 3x minus 2 and multiply that by x to the third minus x squared plus 3x minus 3, multiply those two together, I'll get the polynomial up here. Once again, this is to the fourth power. And so you've probably seen polynomial long division. This is the way that you ultimately do it anytime nice things don't happen. We'll talk about nice situations and the way they can happen. With this method, it is often in math, when we're giving you homework and things of that nature, we try to give you nice numbers so you get nice numbers back out. Fractions are possible, like you need to multiply by a fraction to get things to cancel, so you could have fractional values as your coefficients. But usually that's a sign that something's gone wrong. If you start needing to get these to be fractions to cancel out your leading term every time, you probably made a math error. And with this, since you're changing so many things, if you're not very meticulous about your note taking and working out your problems, if you miss a single sign and you won't know where you missed it, it'll all go horribly wrong. It'll just be mistake after mistake after mistake, and your mistakes will compound, and you could get something that just isn't even close. And I would suggest at that moment, when you start getting horrible fractions back out, I mean, you just get weirder and weirder fractions back out, you stop and start over again. I'm not saying fractions aren't possible. I'm just saying that usually we try to give you nice problems, so you'll get a nice remainder, or you'll get a nice two factors that multiply and to give you what you want. And if you're not in that situation, try starting over. It's the easiest thing to do. Trying to find your mistake can be very, very tedious. Synthetic division is another way of dividing. Synthetic division can only be used when you're dividing the leading polynomial, or when you're dividing a polynomial by a linear factor with the leading coefficient of 1, or when you have, this is your generic form of a polynomial, you have a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus all your intermediate terms down to your constant a sub 0. You divide that by a linear factor, x to the first power here minus k, so that's linear. And so basically what we do here is, since we were keeping track of, if we look at our long division, if we lose all these, if we just keep track of our columns and we don't write down these x's, we don't really need the x's there. We can just have the numbers, right? We know that this is our x column. It's kind of like when you do long division, you have a thousands, hundreds, tens, ones column. Same thing here. It's just we have our powers of x as our columns. So if we keep track of our columns, then we don't need to worry about all this jazz that we have here, and we could eliminate half the symbols on the page. But not only that, when you have a linear factor, you only get the first two, the leading part is the only column you're really keeping track of when you're doing a linear factor. So if you can crunch all that down into this synthetic division setup. So here we have k, and we're going to say k, and so first we bring this, the first term down. This doesn't change. But when we move up and to the right, we're going to multiply it by k every time. And then when we move down, we're going to add those terms together, and then we're going to have a new term here, and then when we move to the right, we're going to multiply by k. We keep doing this all the way down until we get to a remainder. And the remainder may be 0, it may not be 0. And then below here, we'll have a polynomial where this used to be the x to the n column. This will now be x to the n minus 1 because we've reduced the power by 1. So it's one of those things that students look at, and they may have done synthetic division before. It doesn't look familiar, or you haven't done it in a while, but it's really easy to get the hang of. And most students, oh, I hope it hadn't been blurry like that for too long. See if I can't cut that part out. So pretty sure it was fine for this. Synthetic division, another way to divide. A synthetic division can only be used when you're dividing a polynomial by a linear factor with a leading coefficient of 1, or we have our generic polynomial a sub n x to the n plus a to the n minus 1 x to the n minus 1 plus our intermediate terms until we get down to our constant term, divided by our linear factor x to the first power, it's understood there, minus k. We bring down every first term, then multiply it by k, and then add it every step. So when we first term comes down, and then when we move to the right, we multiply it by k, and then add, multiply by k, add, and so forth until we get to our remainder. This was our x to the n column. This now becomes our x to the first column. And I don't know if I got this before. When we had polynomial long division, if we get rid of our, if we just have our columns be our x powers, then we can get rid of half our symbols on this page, and we just keep track of our coefficients. And since linears, linear factors are when I divide by linear terms, it's only going to involve the first column, or this first diagonal right here. And if we keep track of that, we can squish it all down into one synthetic division bar. Like I said, students are usually pretty happy with synthetic division. It's something you can get a hold of pretty quickly, and it's very nice to use. So here, our k is going to be equal to 2, because remember this is x minus k. And then I'm going to say, okay, so I have my synthetic division bar, so I'm going to put 2 right here. and then I'm going to, over here, I'm going to draw a line. And then I'm going to use the coefficient. So this is my x to, so I'm going to have a 1 for my x. So let me label my columns real quick. So I have my x to the third, my x squared, my x, and my constant. Run into that. So now I'm going to have my 1, my 4, my -10, and my -9. Actually didn't need my bar to go out that far. And so now that I have that, I bring the first number down, 1. So I have 2 times 1, so that's going to give me over here, I'm going to bring this up. So grab a different color here. So I'm going to move this up and to the right, and I'm going to multiply it by 2 when I do. Because that's what I'm multiplying by right there. So that's going to get 1 times 2 is 2. I add it this step, I'm going to get 6. Then I'm going to move this up and multiply it by 2. So that's going to give me 12. And I add, -10 and 12 together gives me 2. Positive 2. And then I'm going to have multiply by 2 when I move it over. It's going to give me 4. And then I'm going to add these two together, and I'm going to get -5. So what happens here is that, once again, like I said before, this was my x to the third column. This now becomes my x squared column. And I now get the polynomial 1 times x squared. We don't need the 1 there, but we can write it there for now. Plus 6x plus 2. And now my remainder becomes plus. And I like to keep the sign, the negative, with the number. And say plus this over what it was divided by. And that's x minus 2. So once again, we don't need this 1 here. I'm going to say it's x squared plus 6x plus 2 plus -5 over x minus 2. So that was our synthetic division. And we'll be doing it a lot in the next section as well. Alright, so this one's a little bit more interesting because if you notice, we've skipped powers of, once again, this is supposed to be a square, pretty sure. That's supposed to be square. And so we skip powers of x. So we're going to say this is, x plus 3. K would be equal to -3. So we're going to have our box, -3 in it, and then we're going to have our synthetic division bar. And so right above these, I'm going to write, this is going to be our x to the 8th. X to the 7th, x to the 6th, x to the 5th, x to the 4th. I always do this. I always run out of room every single time. I think I plan for space, and then I don't. And this is our constant column last. So I'm going to try to line all these up. So our x to the 8th column is going to have a 3, x to the 7th is 9. Then we're going to have a 0 for x to the 6th, 0 for x to the 5th, 0 for x to the 4th. And then we're going to have negative x to the, so we're going to have -1. Then we're going to have -3, so that's my x squared. Then I'm going to have 1 and -1. So this is what I have. So now I'm going to, first thing I do is I'm going to bring down this 3. So that becomes 3 here. -3 times 3 becomes -9. Add these two together, I get 0. So now here's some interesting things that happen. I get -3 times 0, which gives me 0. Bring 0 down. -3 times 0 is 0. Add my zeros. Get 0. -3 times 0. Get 0. -3 times 0. I get 0. And then now I'm going to get a -1. So -3 times -1 gives me +3, which is going to give me 0. And then I'm going to get 0, 0, 1. Comes down. -3 times 1. And that's going to give me -3. And then my remainder is going to be -4. So now this becomes my x to the 7th column. So I get 3x to the 7th. And then I don't get another one. And then remember, this was the x to the 3rd column. I reduced the power by 1. And it's going to become -x squared. This is going to become x, 0x. And this is going to be plus 1. And then I'm going to say plus minus -4 over x plus 3. So it's just important that you remember to skip every power. If you're missing a power, you need to skip a space, use zeros. Try to line up all your columns very well. so you're not overlapping. And then remember, everything gets reduced by 1 power in the next row down. So this becomes an x to the 7th column, this became an x squared column, this became the constant column, and this constant column is now the remainder. Alright, so remainder theorem. So if we divide p of x by x minus k, we have p of x equals x minus k times q of x plus the remainder r. When x equals k, that gives us the following. So we have p of k equals k minus k, because we replaced that x with k. This zeroes out, so our quotient zeroes out. We don't care what that is. And all we'll get is the remainder with k plugged in. So in other words, we can evaluate pk by dividing p of x by x minus k, and then evaluating the remainder of k. So the remainder is 0, then x minus k is a divisor of p of x, and so p of k is equal to 0. So why is this useful? Well, basically, if we want to determine this, so look at this next exercise. If we have this exercise here, using synthetic division, we can determine whether 5 is a 0 of p of x equals 4x to the third minus minus 15x squared minus 10x minus 21. If it is not, compute the actual value of p of 5. So before, we would actually have to plug in 5. Now, modern day, we have computers and calculators that can do everything. Usually algebra students can. But back in the day, you wouldn't want to raise the number to a power unless you had to, especially if it was a decimal. So to avoid that, if you use a remainder theorem, I can just use synthetic division to find out what the remainder is. I don't have to plug 5 in. I can just say I have 5 here, so my k is equal to 5. So I'm going to say 5 here, and then I'm going to have 4 minus 15 minus 10 minus 21. So this is our x to the third column, x squared, x in our constant column. This is our k in there. And so now that I have that, remember I used 5 because x minus 5 would have been what I'm dividing by if I'm plugging in 0, if k is 5. So I'm going to bring this 4 down. So I'm going to get 20. 4 times 5 is 20 minus 15, and I'm going to get 5 again. And then I'm going to get, did I do that right? 5 times 5, which is 25. And so that's going to give me positive 15. And then I'm going to get, making sure I did this correctly. I changed my example. I think my numbers are larger than it should be. But then I think I should get. So 5 times 15, and that's going to give you 5 times 5 is 25, plus 50 is 75, and then my remainder, which is going to be negative 21, or 75 minus 21, which is going to be 40, and that's going to be 54, I think. So 54, positive 54 is remainder, so p of 5 is 54. Alright, so it wasn't a 0. And like I said, we could have found this out by plugging in 5 to the third minus 15, 5 squared minus 10 times 5 minus 21. We could have figured it out this way, but it would have been a very, very huge number. These numbers would be very huge, and then we just get 54 at the end of it. Alright, one other thing in this section is find the equation given the roots. So if we want to find an equation that has given roots solutions, for example, we want to find an equation that has the roots x equals negative 5 and x equals 3, we proceed as follows. We rewrite the linear equation with 0 on one side. We have x plus 5 equals 0 and x minus 3 equals 0. So in other words, we just move this negative 5, made it positive 5, move this 3 to the other side and make it negative 3. So now we have two factors. We multiply the two factors from step 1 together to make the product equal 0. So we have x plus 5 times x minus 3 equals 0. And so we now have a polynomial with these as the zeros or roots of them, or negative 5 and 3. are the zeros. If we give any more information, such as the end behavior or the y-intercept, this will not change the factors, but we may need to add a multiplying coefficient. So here we have our first example. So I'm going to construct this. So we have a 0. So I have zeros at, so I'm going to worry about this later, but if we have zeros at x equals -5, x equals 1, and x equals 2, that means we have the corresponding factors. So I'm going to have, for my generic polynomial, I'm going to have f of x equals a, this is our unknown coefficient, and then we'll have our first factor, which is going to be x plus 5, because that'll give us x minus 5 as one of our zeros. Then we're going to have x minus 1, because that's going to give 1 as one of our zeros, and then x minus 2. So this has all the correct zeros, -5, 1, and 2. But my leading coefficient may control what happens. So it says, as I'm on the x-axis, right, and I'm going to positive infinity on the x-axis, my function goes to, my f of x goes to negative infinity. So in other words, it goes down, right? My function is going down. So in order to go down, that means the leading coefficient has to be negative. So that means let a equal -1. So f of x goes to negative infinity as x goes to infinity. And so now I'm going to get f of x. I have a negative out front, and then I have all my zeros. Now, one thing that will happen with the Hawks courseware is oftentimes if you get this wrong, you say, show me the answer, it will multiply this out. You do not have to multiply this out. You can enter it factored. Not only that, if the only other condition is that it has to be negative, sometimes they'll change this to a 5 or a 4 or a 2, you know, like -4, -5, -2. It's the same polynomial. It satisfies the same zeros and ending condition for f. So you may see that where you're like, I got a -1 and they got a 5 and they got a -5, but it still worked. It could happen. Sometimes Hawks generates random stuff like that. It should work fine. But remember, you can enter your answers factored, and remember that for your tests as well. You want to enter those numbers factored. You don't want, or those polynomials factored. You don't want to multiply them out. This one's very similar. So we have x equals -3, x equals -1, x equals 3, and x equals 5. So our generic polynomial will be f of x equals, and then we'll have our a, our unknown leading coefficient, and then we'll have x plus 3, x plus 1, x minus 3, and x minus 5. So see how that lines up? We move the -3 over. That -3 was 0. That means x plus 3 was a factor. -1 is a 0. X plus 1 is a factor. 3 is a 0. So x minus 3 is a factor. And 5 is a 0. So x minus 5 is 0. Now they say if we were to plug in 0, so a y-intercept means that x is equal to 0. If we plug in 0 for this, what happens? Well, I'll get a times 0 plus 3, 0 plus 1, 0 minus 3, and 0 minus 5. So basically I'm going to get a times 3 times 1 times -3 times -5. Put parentheses around these. And so I have this, and so basically I'm going to get 3 times -3, which is -9, times -5, which is going to be a times 45. And so I'm going to get 45a back out. Now what should I have gotten? I should have gotten 15. So this needs to equal 15. So that means if I divide both sides by 45, I'm going to get 15 over 45 equals a, or 1/3 equals a. So in other words, I need to have a leading coefficient of 1/3 for this polynomial. So I need to have f of x equals 1/3 times x plus 3, x plus 1, x minus 3, x minus 5 for this to work. Otherwise, I won't get the right y-intercept. So if they give you a y-intercept, you're going to have a particular number come out. It could be positive, it could be negative. In this case, it was positive. But yeah, so you'll get a fraction back out. Or you may get a whole number depending on your problem in Hawks. But remember, you can write it in as factored. You don't need to multiply it out because nobody wants to multiply out for binomials. That would take a while, and the chances of making a mistake are pretty high unless you're using some system to help you solve that or help you multiply that out. So enter it factored. Hawk should take it factored. But remember, they'll show you the answer, the correct answer, as an entire polynomial. Don't know why. I've asked for years that they not do it that way, but they do. So be aware of that. Unless they change it this summer or whenever after this video is made. That's the lesson for today. Thank you all. Have a great day.